Welcome back. We are in the next tutorial in electric power system. Here we will discuss the problems related to Gauss-Seidel load flow analysis, the important formulas that will be useful for solving the problem in Gauss-Seidel. So we know that the complex power S is basically equal to E plus JQ, and this is equal to the voltage and current conjugate. So we can get the real power of a particular bus I and the reactive power of a bus I using splitting of these complex power, where the conjugate whatever we have on the current side can be shifted to the voltage with a negative sign here in Q. So you can observe here that a negative sign is there in the Q because we are dealing with the voltage conjugate and not the current conjugate. So these two expressions are the fundamental expression that we need to use for the Gauss-Seidel as well as the Newton-Raphson load flow analysis. We will discuss in the next tutorial the problems related to Newton-Raphson. Here we will discuss on the Gauss-Seidel analysis. The Y indicate the admittance and IK indicate the mutual admittance between the two buses I and K, where the voltage of that two buses are Vi and Vk. So we have the magnitude here. So we are dealing with only the values of the voltage and the admittance, and the angle is basically taken care with respect to the cosine and sine component for the real power and the reactive power. So here the theta del are the angles of the corresponding admittances and the voltage. So what we need to remember is that a negative sign should not be missed in the reactive power. Active power we have positive sign, and here we have cosine term in active power and sine term in the reactive power. When we calculate the change in the power during the calculation stage for the active power and the reactive power, then what is the injected power minus the calculated power, where the injected power or the scheduled power is basically the difference between generator and the load power and whatever you get at the calculation value. So the difference of each power, whether it is real and reactive, we need to take care in the corresponding iteration of the Gauss-Seidel method. So again, this power expression, which is the complex power expression, if we segregate and expand it, we will be getting in the expression of the voltage, and basically the current is divided into admittance into voltage, because we know that the current is the product of admittance and voltage. This is again coming from the Ohm's law. So for those who are not knowing this expression, for then I'll tell, since you know that V is equal to I into Z, so if I divide this Z and take in the denominator, I'll get the admittance, and hence I'll get the current expression as the admittance into voltage. Now, since we got this admittance equal to current into voltage, so it means that the voltage into current conjugate will give me the power S. And now here, if you see the current conjugate, if we do it, then we will be getting it in the term of the voltage conjugate. So that expression we are going to put it here, expand it in the form of admittance and the voltage. The voltage of a particular bus Vi then can be obtained from this expression arranging in the form of real power and the reactive power. So here this expression is giving us the voltage of a particular bus, and this is what we need to iterate, because if you observe on the left hand side we have the voltage expression, on the right hand side also we have the voltage expression, and we need to update this voltage at each iteration so that the new voltage can be achieved. Now the power of each iteration of the buses also need to be updated, and to make the calculation faster, we have the voltage acceleration factor lambda, which will iterate at each iteration and make the calculation faster, where K indicate the iteration value, whether we are in the first iteration or the second iteration. The theory part of this entire discussion is discussed in detail in the lecture class. Let us go and solve the problem. So before we solve the problem, let us understand this algorithm, what is Gauss-Seidel load flow and what are the steps that need to be followed. So if you have a system which is only involving the PQ buses means the load buses only, then in that case, the first step would be to form the Y bus matrix from the given line data. So here you will be having the single line diagram, and in the single line diagram, you will have all the impedances value Z that you need to convert into the admittance Y. If the admittances are given, then one step will be reduced. Second step is basically to assume the voltage of each buses as 1 plus J0 for all PQ buses, that is the load buses. This is known as flat stat. So we are doing the flat start because the voltage Vi we are assuming at magnitude 1 with angle 0. Now we need to update the voltage of the load buses using the expression that we have seen in the formula. So for k plus 1 iteration, we can update from the kth iteration what is the voltage. So from this value, we will go to this value and keep on iterating it to increase the voltage with the reduce error. So to accelerate this voltage to improve the convergence, we have the acceleration factor lambda, which we need to use it. This lambda will be given in the problem. Usually this value may be 1.5 or 1.6 depending upon the nature of the problem. So we will see how the lambda is specified. And then we need to check for the convergence. If the difference between the two iteration value k plus 1 and k is less than certain threshold value, so this threshold value can be 1e minus 5, then we have to stop it, the problem, and we need to say that the convergence has achieved. So if it is stopped, then otherwise go to the step number 3 and keep on iterating. Now the second, if the system is involving both PQ buses as well as the PV buses, where the PV bus are the generator bus, also known as voltage control buses, then you need to form first the Y bus matrix from the line data, which is common step for both one. Again, you have to assume the voltage of a particular bus I as flat stat from 1 plus J0 for all load buses, and the angle of the bus can be assumed as 0 for all the PV buses. Now, if the bus is PQ, because here we have the combination of PQ and PV bus. So if the bus is PQ, which was the previous step we have seen, so we need to update the voltage of the load bus Bik plus 1 with the previous step k, iterating it and updating the solution. But if the bus is PV bus, that is a generator bus, then Qi is not given in PV bus. So the reactive power of the generator bus is not given because only the real power and the voltage magnitude is given. So we need to find out what is the reactive power of the PV bus at k plus 1 iteration using the formula given this one. So here you have the imaginary value of this is a complex number. So this complex number imaginary value we need to take with a negative sign that will give me the reactive power value. Now this reactive power is very important because we need to check whether this reactive power is lying between certain limit between the minimum and the maximum value. So if it is not violating, then only we have to proceed. If it is violating, we need to go to the other step. So now you update the voltage Vik plus 1 with respect to the voltage Vi, because here the reactive power Q, which is we have obtained by checking the limit whether it lies between the lower limit and the higher limit. Now this voltage magnitude is already given and we need to find out the voltage of k plus 1 iteration using this formula, that is the correction factor multiplying with k plus 1 iteration to the voltage. Now if the Qi, whatever we have estimated here, it is violating the limit, and then if the Qi is less than Qi minimum, then we will set the Qi to be the minimum value. If Qi is greater than the maximum, then we will set the Qi to be the maximum value. So these values we need to check whether it is violating the reactive power limit or not. So treat the bus as PQ bus and update the voltage. So if it is violating, then the PV bus will become the PQ bus in assumption, and we will update the voltage both in magnitude and angle according for this iteration. So once we have checked this, now to improve the convergence, we can increase the convergence factor. This is again the convergence factor. Earlier we have taken lambda. Lambda and alpha is same. So we need to check for the convergence whether it is less than the threshold value which we have set. So threshold value can be set at any value 1e minus 5 or 1e minus 6 depending upon the problem. If it is yes, then stop it and otherwise go to the step number 3. And then the final step is the calculation step, where you need to calculate what are the line flows, what are the losses, and what is the slack bus power. So these calculation will become at the final state once you have obtained all the voltages and the current. Let us see the first problem in Gauss-Seidel analysis. So using the Gauss-Seidel method, determine the phasor values of the voltage at bus 2 and 3. So if you observe this diagram, you will be seeing that there are 3 buses, bus number 1, bus number 2 and bus number 3. So there are 3 buses, and it is said that consider the slack bus, which is the reference bus, to be the bus number 1. Remember here, the slack bus will be that bus which is one of the generator bus. The third bus cannot be a slack bus because it is basically the PQ bus, and the second bus is a PV bus, and the first bus is also PV bus because a generator is connected to bus number 1 and bus number 2. So slack bus, which is a reference bus, in electrical circuit we take the ground as the reference, 0 volt. So that is basically here analogy is basically the slack bus. So slack bus is that bus which is the reference, which you have to take either of the generator bus. So here in the problem it is said take the slack bus to be the bus number 1, and 2 is basically the generator bus. Now all the impedances which is connected between the various buses 1, 2, 1, 3 and 2, 3. So you can see it, the line connecting between 1 and 2 is this one. So this is the impedance Z value which is given here 1 and 2. Similarly, what is the impedance connected between Z23, what is the impedance connected between Z13 are basically given by these data. You know that impedance is basically complex number which is given by R plus J times X. So the real values are the resistances and the imaginary value are the reactances. So we need to find in the second step the slack bus real and reactive power. So this is the slack bus. What is the real power P and the reactive power Q for after the second iteration? It means the problem itself is saying that stop after second iteration, no need to find the third or the fourth step. And then finally, what is the line flows, what are the line losses after the second iteration if you neglect the line charging admittance. So line charging admittance means there is a capacitor which is connected between the bus and the reference bus. So here it is said that line charging admittance need not to be considered. So there is no y by 2 value which will be seen in the later problem. Now apart from these line impedances, some other data is also given, which is the scheduled generation and the load, assuming the bus voltage for the sample power system. The base MVA rating of this bus is given as 100 MVA. So we have to take 100 MVA as the base power. So bus number 1, bus number 2 and bus number 3, where bus number 1 is the slack bus number 2 is basically the PV bus, and bus number 3 is basically the load bus, that is the PQ bus. So we need to assume certain voltage, and this assumption is already given in the problem. This is a flat start. What we need to do it at 1.05 J0 for the slack bus and 1 plus J0 for the PV bus and the PQ bus. The generation and the load which is connected at the buses, if you see, so it is the real power P and the reactive power Q for the generator, and the load is given in megawatt and megavolt ampere reactive for the generator and the load. So for bus number 2, if you see it, then you will find that this value 50, which is the real power, plus J times 30, which is the reactive power, is basically for bus number 2. Bus number 3 is basically the load, which is 0. Similarly, the bus number 2, the load is also connected. So if you see in bus number 2, both generator is connected as well as load is connected. So it means the total power will be equal to the generating power minus the load power. So this is what we need to take. So similarly, in the PQ bus, there will not be any generator, only there will be load power. Let us see the problem, how to solve it. So the first step in solving this type of problem, the initial computation will involve the computing the per unit values from the actual value what is given to us. So since the base value is set to take 100 MVA, so this is what you have the base power. So determine the power of the different buses, the generator and the load bus, the real power and the reactive power with its actual value by the base value. So actual value is given as 305.6 and the base value is 100. So if we divide these two value, we will get what is the per unit value of the second bus and the load generation. So similarly, we can obtain for the other powers, real power and the reactive power for bus number 2 and bus number 3. So now once you have obtained these values, then the generation per unit values you will be obtaining means the load and the generator, all values has to be converted in the unit of per unit value. Once you have done it, now the net injected power. So net injected power is basically the total generation minus the total load. So what is the generation minus load for the second one? What is the generation minus load for the reactive power and for the third bus and the second bus? So these per unit value you need to obtain, because all calculation has to be done in per unit values. Once you obtain the per unit values of power, next step will be to form the Y bus matrix. So Y bus matrix, whatever we obtain, so we have discussed how to form the Y bus matrix. So Y bus matrix is basically n cross n matrix, where n is the number of buses, and here what the diagonal elements you have y11, y22 to yn. These are basically summation of all the elements which are connected with yi, I equal to 1 to n. So these diagonal elements is basically sum of all the lines. Like for example, if you see the bus number 1, you may have two lines which is originating from bus number 1. So summation of these admittances will be giving you the admittance of y11. Similarly, if you have the second bus, what are the lines which is originating from the second bus? All the summation will give you y22 and so on. Now the common element, like for example y12, y13, these are basically the admittance which is connected between the two lines with a negative sign. Okay, so since the given value is basically the impedance value, so we are taking the reciprocal of that to find the admittance. So find the reciprocal of these values to obtain the admittance. Admittance matrix will be symmetrical in nature. So once you have computed 1, 2, it will be equal to 2, 1, 1, 3 will be equal to 3, 1, 2, 3 will be equal to 3, 2. So these values you will be getting as the admittances. Similarly, you can obtain the admittance of the diagonal elements, as I said you here, yi, which is summation of all the admittance which is connected between ik, where I is varying from 1 to n. So 1, 2, 1, 3 and so on. Here you note here, this is the value which is connected as line charging admittance. And the problem says that there is no line charging admittance. So this value will be equal to 0. We don't have any line charging admittance. If it is given in the problem, you need to take this value also. So you obtain all the self admittance. So this is what is called self admittance, and this is known as the mutual admittance. So self and mutual value we have to obtain it. Once we obtain, we can convert that in polar form with magnitude and phase, or the phasor form, and we can obtain the Y bus. So Y bus is nothing but n cross n bus with all values of admittances, and these values are basically the per unit value. So these are per unit values, whatever we have got it. Now we have to use these value for the calculation purpose. Now let us see, the calculation will start from the third step, where the iterative computation starting from the second bus. 1 is basically the slack bus. So this is the reference bus. 2 and 3 are the remaining buses. One is the PV bus, another is the PQ bus. So we have to find the iteration P plus 1. So P is the iteration value for the second bus and the third bus depending upon the initial iteration P. Okay. And this formula we have seen the basic formula. It is said in the problem that the slack bus voltage V1 is 1 plus 0.5 plus J0. This is the flat start that we are doing for the different buses for the second bus and the third bus with the 0th iteration or the initial start. This voltage is already given to us. Now this basic formula we will use and we will substitute the values of the power, the admittances and the voltage whatever we have in the problem in the formula. So we have already obtained all the values whatever is needed, and step by step we need to do this calculation substituting the values of the power and the admittances. So we have already obtained Y bus matrix. Now Y bus matrix will give us the value of Y22, Y21, Y23 and so on, and the power P2 and Q2. So we can obtain the expression of the voltage of the second bus at the P plus 1 iteration with the initial values at P. Okay. So this is the expression that we have got it substituting all the known values that we have computed. Now similarly we can do this one for the third voltage, and we can get this expression substituting the values of the admittances and the power whatever is required. Once we have obtained this voltage, we can obtain what is the voltage of the first iteration. So voltage of the first iteration will depend upon the voltage of the 0th iteration, which is the initial value, which is 1 plus J0, and we can obtain after the first iteration what are the values of the second bus and the third bus voltage after the first iteration. So after the first iteration we are getting these values, and if this calculation is taken further, so for the second iteration for the bus number 2 and 3, the initial value we will be taking the voltage of the second bus, the first iteration. So this we have to put it in the expression. So after second iteration we are getting these values. I'm not discussing in detail about this calculation which is already seen on the slide. You can note down these values and you can obtain these voltages of the buses after the second iteration. Now we have to stop our calculation in the second iteration as the problem suggests, and we have to compute certain other values of the losses and the power. So what is the computation of slack bus power after the second iteration? We are stopping at second iteration means it is given in the problem. Otherwise we can carry forward and stop it for the threshold value of sigma. We will see that in detail in the other problems. So here the problem we can obtain the power of the bus number 1, which is the slack bus, using this formula of the power expression where the bus started from k equal to 1 to 3 because we have 3 buses. So all the voltages value and the angle values we have to put it, and here we have the cosine expression because we are finding the real power. So all these values we can get it from the calculation that we have done in the previous step and substitute that in this expression. We will get what is the real power. So real power we will get as 3.84 per unit. So you can solve these steps to find the power as 3.84 per unit. Remember the unit will be per unit because all calculation we are doing in per unit system. Now to convert it into actual value, we have to multiply that with the base value which is 100 MVA. So we will get the actual power which is 384 megawatt for this real power. Similarly, the reactive power we can obtain where we have the negative term here to be taken into account, the sign expression has to be taken into account, and remaining formula remain the same. So we will get the per unit power as 1.9786, which we can multiply with 100 to get the unit in megawatt reactive. So this will be megawatt reactive power for the bus number 1, which is the slack bus. Now, the line flows and the line losses that we need to calculate is basically coming from the expression of the power which is involved between the two buses IK. So because we have to calculate the line flows, we need to take two buses into account IK. So this formula was given in the formula slide. So we can obtain the power P12, P13 and P23. All the lines which are connected and shown in the single line diagram. So we will be getting the power of the lines in per unit for the different lines which are connected between 1, 2, 2, 3 and so on. So these values we have to obtain, which indicate that what is the line power between the two buses. So IK. Once we have obtained this, we can calculate the power losses in the line. So power losses in the line is basically the power if we are calculating for 1, 2, that is P12 plus P21. Now you can know that P21 because we have to take a negative sign here. P31 will have a negative sign here and P32 will have a negative sign. So we can obtain the power loss. So power loss again will be in per unit. So this is the per unit value and then we multiplied with 100 to get what is the megawatt rating. So because the base value is in megawatt. So this is the problem where we discuss the real power line losses. We can continue this to find the reactive power losses of the lines which are involved in per unit with the expression that is given in the formula slides. So these values are basically the reactive power involving the different buses, and then we can calculate the power losses in the line per Q. So again we will get in per unit value. So this per unit value we have to convert it into megavolt ampere reactive multiplying with the base value which is 100 we are taken in the problem. Okay, so it is similar to the real power calculation, only the reactive power we have to substitute. Problem number 2, where we are given the system data for a load flow solution. So these values are given between the various buses. Now note here carefully that this value is given the admittance. In the previous one, it was given the impedance value. So we have to obtain the impedance as the admittance. But since here admittance is given directly, so we need not to do that. We can directly use this data in the calculation. Similarly, the active and the reactive power P and Q for the different buses. Now here if you see there are 4 buses. So Y bus matrix whatever we will have is basically 4 cross 4 because we have 4 buses. And the first bus is a slack bus which is the reference bus, and all the buses if you see it, this is the load bus. Okay, and you do not have any PV bus or the generator bus in this problem. Also note here that the single line diagram is not given in this problem because it is already mentioned these values. So you can easily find out the connection between the different buses and their corresponding admittance value. Determine the voltages at the end of the first iteration using Gauss-Seidel method. This is the acceleration factor 1.6 that you need to take to accelerate and get the answer in a fast way. Let us see the solution. So first we need to obtain the admittance matrix similar to the previous problem with a difference that you need not to take the impedance value directly, we have to take the admittance value. So this is equal to Y11, this is Y22, Y33 and Y44. So these values are basically the self admittance. These are the mutual admittance. So mutual admittance will have a negative sign. Please take into consideration this, okay, which is common between the two lines. So what is the common between 1, 2, what is common between 2, 3 and so on. And this will be symmetrical because if you see the value of Y13 is equal to the value of Y31. So it means it is a symmetrical. Whatever the value will get Y12, the same value will get Y21. Now we will start our calculation from load bus power and which need to be considered negative. Generator bus powers are positive. So load is basically consuming the power. So we are taking the negative value of the power. So what is the voltage of the second bus first iteration? We need to compute from the initial value of 0. So these are the initial iterative value. So what we are getting is basically the voltage of the first iteration for the second bus. Now we can accelerate this calculation using the acceleration factor 1.6 in the formula. So you can see in the formula slide we have given this acceleration calculation using the acceleration factor. So we will get what is the voltage of the second bus after the first iteration. In the problem it is said stop the calculation after the first iteration. Similarly, the voltage of the third bus after the first iteration, we have to take here the voltage of the second bus first iteration, voltage of the fourth bus 0th iteration. Why? Because second bus already we have calculated in the previous step. So we are taking the first iteration. But fourth bus we have not calculated yet. So we will take the 0th iteration. And then we can substitute and find out the value of the third bus first iteration. Again, using the acceleration factor 1.6, we can find out the voltage computation faster for the iterative process. Again, we have to stop after the first iteration. Similarly, we can do for the fourth bus, its calculation in the first iteration. So we have to take the second bus first iteration and the third bus first iteration because we have already calculated that. So this is the value that we will get. Note here this is in per unit. And this is the acceleration factor with the acceleration factor to be 1.6. Problem number 3, which is the extension of the problem for the second. If the bus number 2 is taken as generator bus. Remember, in problem number 2, the second bus, third bus and the fourth bus, these 3 buses were the PQ buses and there were no PV buses because one is basically the slack bus. So if we take the bus number 2 as the generator bus, so the second bus is a generator bus, it means 3 and 4 are PQ bus. The voltage of the second bus is 1.04 and there is a reactive power constraint that we need to obey from 0.1 to 1. Lower limit 0.1 and higher limit is 1. Determine the voltage starting with the flat voltage profile assuming the acceleration factor to be 1. So alpha value we can take as 1 and we need to compute it. So how the calculation will proceed? Let us see. Since the bus number 2 is now the generator bus, which is the PV bus, Q2 is not specified. So there is no Q2. We need to calculate the Q2. Power 2, we have already seen it is 0.5. Determine the voltage of the second bus first iteration by first computing the reactive power Q2 and using the voltage which is given 1.04 J0. Initial phase angle had to be taken as 0. So the power expression P2 minus JQ2 is this one. So first we need to calculate the Q2. Once we obtain the Q2, this Q2 we can put it in this expression. So Q2 is nothing but negative of the imaginary of the complex number, this one. So all the values we have already seen in the previous problem, we can put it and find out what is the reactive power. Now note here, this reactive power is 0.1108 and what was the limit given in the problem that you need to check. So Q2 is within the limit because the limit was 0.1 to 1 and it is lying between that range. So Q2 is within that limit. So the voltage V2 is set to V2 specified with the same phase angle. So V2 now we have to calculate using the formula where the voltage of the third bus and the fourth bus 0th iteration we will take because here we are finding for the first iteration. So bus 2 is a generator bus now. P2 and Q2 are positive because it is a generator. If it is a load then it will be negative. P2 is taken as specified and Q2 as calculated. So Q2 we have obtained 0.1108. So here we can put it the Q2 value. P2 is 0.5 and we can obtain the voltage of the bus at the first iteration what we got it. So this is the voltage what we got it. Delta, the phase angle is 1.59. Convert this one into phasor form, you will get this angle. So voltage is 1.04 angle 1.59. Okay. So this is the voltage of the second bus after first iteration. Similarly, we can calculate the third bus and the fourth bus after the first iteration. So we can obtain these values. Remember, the third bus and the fourth bus is basically the PQ bus. So we will have a negative sign here. Okay, so this negative sign will become the positive because you have basically P minus JQ. So if you take negative, it will be minus P plus JQ. So that has to be taken very effectively. Problem number 4, which is again the extension of problem number 2. If the reactive power constraint is lying between this range, what will happen in the problem at the end of the first iteration? So here the lower limit, if you check, 0.22 it is. Earlier it was 0.1. So in this problem, since the voltage after at the initial guess was 1.04 and Q2 already we have calculated as 0.1108 in the previous problem, it is less than the minimum specified. So minimum is 0.2, but what we got 0.1108. So reactive power generation for bus number 2 is fixed. So the reactive power we have to take 0.2 and not 0.11. This is the lower limit that we need to take because it is violating that limit. Bus 2 treated as a load bus for this iteration. So bus 2, which was initially the PV bus, since it is violating this limit, so the PV bus will become the load bus, and then we have to calculate it starting from the flat stat of 1 plus J0. So these assumptions that the specified quantities are P and Q, unknown voltage are the voltage and the phase angle, generator bus P and Q are positive and load bus P and Q are negative. This we know it. This fundamental we have to use for solving the problem. So the voltage of the second bus after the first iteration. Now remember, this is not a PV bus. This is a PQ bus now because it has violated the limit where the reactive power Q2 is basically taken 0.2 and not 0.11. Also, since it is the PQ bus, you will be taking minus P plus JQ in the calculation. So you will get the voltage of the second bus after the first iteration. Similarly, what is the third bus after the first iteration and the fourth one can be calculated in the similar manner. So reactive power violation is very important, whether it is lying between the lower limit and the higher limit. If it is violating the lower limit, you take the lower limit. If it is violating the upper limit, you take the upper limit for the calculation. Problem number 5, let us see how it is different. So here you have the 3 buses, 1, 2 and 3, where this is basically the PV bus 1 and 2 and 3 is the PQ bus, which is a load bus. Power is basically tapped here. So since it is a 3 bus, so you'll have 3 cross 3 matrix and the bus codes are given and their corresponding impedances R plus JX. So Z is equal to R plus JX. These values are given. Also, the line charging admittance Y by 2 is given. So this was missing in the first problem. As I said you that line charging admittance you need to neglect. But here you need not to neglect it, you have to take into consideration. Also, the bus data in terms of power and voltage and the type. So first one is basically the slack bus. So again I said that one of the PV bus can be taken as slack bus. So it is already given in the problem that take the first bus as the slack bus. Second bus is a PV bus. Third bus is a load bus, PQ bus, and the corresponding power other one is already given in the table. So you have to assume a flat voltage start, determine the voltage at the end of first iteration. So you have to show only the first iteration result using the Gauss-Seidel method. Reactive power limit is 0.222 and the acceleration factor is 1.6. So how do you calculate this problem? Remember here the Y bus calculation now will have the line charging admittance Y by 2. So this is also will be there in your calculation. So obtain these diagonal values carefully because we need to calculate this Y by 2 also. Similarly, also here if you see it, these are per unit. So it is given J. J, what is the meaning of J? J means impedance and minus J means admittance. So since it is given J, it is the impedance value which is given. It's not the admittance. So you have to convert this into the admittance. So admittance is 1 by impedance. So obtain the Y bus and then start with the first iteration. Bus 2 is basically the PB bus. Determine the Q2. So Q2 limit you have to find out, which is 1.028. Now if you see it, the lower limit is 0.2. So here it is 1.02. So it is within that limit. It is not violating it. So modify the voltage V2 now. So voltage of the second bus after the first iteration you have to take it. What is voltage the second bus? So second bus is basically the PB bus. Okay. So you need to take the Q, whatever you have obtained in the previous values, with the voltage of the first bus in the first iteration, and this is 0th iteration, whatever you have. So this will give you the voltages. So this will be 0 and then voltage is fixed. So determine the correction factor using this formula. So this is given in the formula sheet. You can see to find the voltage. Bus 3 is a PQ bus. So update the voltage of the third at the first iteration. You will be having negative sign here. The change of the sign will be there because it is a PQ bus or the load bus. You take the first bus, first iteration, this is already calculated. Second bus, first iteration, already calculated. So you'll get what is the third bus, first iteration. This is the value you will get it. Also acceleration factor you want to use. So alpha value, which is 1.6. You can find out what is the third bus after first iteration. This is the last problem. Problem number 6, quite an interesting problem. It is similar to the first problem with some difference. So let us see. So there are 3 buses, 1, 2 and 3. 1 which is the PB bus, but since it is to be considered as the slack bus, so the voltage is 1.05 angle 0. These values are basically the impedance values of connected lines, and 3 is basically the load bus PQ, 2 is also the load bus PQ. And here if you see it, the values of the real power and the reactive power is given for the second bus and the third bus. So from this single line diagram of a 3 bus power system, where the generation is located at bus number 1 and bus number 1 is slack bus, you have to take. The scheduled loads are given, line impedance. Now 100 MVA is the base which we need to take into consideration, and line charging susceptance are negligible. So we need to take the line charging susceptance. So using the Gauss-Seidel method, calculate the phasor values of the voltage at the load bus 2 and 3, which are the PQ bus, of 4 decimal places. So second bus and third bus, PQ bus, we have to obtain what is the voltage. Determine the real power and the reactive power of the slack bus. Determine the line flows and the line losses, and power flow diagram you need to draw it of this single line diagram. So this is the single line diagram. What is the power flow diagram? So that's the difference. Let us see it. So again, the problem starts calculating the admittance matrix. So convert all impedances to admittances with these values which are given between the lines. So you have to obtain the admittance matrix by bus, and then your problem will start calculating from the PQ bus of the power of the second bus and the third bus. Then bus number 1 is basically the slack bus. So the 0th iteration voltages are already given. This is the initial start, and you need to obtain the second bus first iteration we need to obtain and find out the values. Okay. So that calculation we have to do it for the third bus first iteration, and for the second iteration for the second bus and the third bus, if you see it, this calculation, so we need to take whatever the voltages we have obtained here for the third bus and the second bus and put it in this calculation. We'll get the second bus and third bus for the second iteration. Now once we have obtained the values, we can see the process will be continuing and the solution will converge with an accuracy of 5 into 10 to the power minus 5 after 7 iteration. So total 7 iteration after the values will converge. So what is the voltage of the second bus after third iteration, fourth iteration, fifth iteration, sixth iteration and seventh iteration is given. Voltage of the third bus after the 7 iteration is also given. So this is what we got it after the 7th iteration, and these values can be converted into its phasor form. So this will be the per unit value. Now the slack bus, which is the first bus, you can obtain the power, and hence the power P1 and the power Q1 in first the per unit and then in megawatt. So this is multiplied with 100 because the base value is 100. So we can obtain the slack bus real power and the reactive power from the data what we have in the problem. Now we can obtain the current. So this is different what we have not seen in the previous problems. What are the line flows? So to determine the line flows, first you need to calculate the line current. So current is nothing but the admittance multiplied with voltage. So if you obtain the current I12, which is admittance Y12 multiplied with the voltage, so that delta V, which is V1 minus V2, and here you will have V1 minus V3 for the current I13. Similarly, V2 minus V3 for current I23. Multiplied its admittances, whatever you have, 1, 3 and 2, 3. Also note that the current I21 will be equal to minus of I12, I31 is minus of I13, I32 is minus of I23. So we can calculate all this current. Once we calculate the current, we can obtain the admittance flows, line flows. So complex power S is equal to VI conjugate. So we can obtain these powers, whatever is involved with different lines with the formula of VI conjugate. So V1 I12 conjugate, V2 I21 conjugate for S21, V1 I3 conjugate for S13, and so on and so forth. So you will be getting all the powers which are involved in the complex power. Now this complex power is nothing but E plus JQ. So the real term is in megawatt and the reactive term is in megavolt ampere reactive. So once you got that, the power line losses you can calculate between the different lines and express that as the losses. Now you are in position to draw the power flow diagram with starting from the first bus, and then you have the second bus, and then you have the third bus. So the first bus is basically was the PV bus. So what are the real power and reactive power of the PV bus? What are the load power of the second bus? What are the load power of the third bus? And what is the line losses of the different lines? Each are given in the power flow diagram from the single line diagram. So these complete our discussion on the load flow analysis using the Gauss-Seidel method. See the lecture first and then solve the problems. It will be easy to understand. Next tutorial with its see on Newton-Raphson method, how to solve the problem. Thank you for now.